Let's say the current is equal to 1 amp and the radius is equal to 2 meters. We can find out what the magnetic field is at x equals to 3. So you go like this. So this is radius is 2 meters, and then 3 would be over here. Right? What would happen? Well, I would just use this equation basically, right? You have B is equal to 2, mu 0 is 4 pi times 10 to the minus 7. The current is 1 amp, divided by 4 pi. One of the r's, this r always comes out, so it's just the radius. You have 2 meters. And then the rest is just simply an integration. And theta to the power 3/2. We get an integral similar to the integral that we got for the electric field, but there are certain things that are slightly different, okay? So this integral reduces to 0 to pi over 2, 2 plus 3 cos theta. Of course, you have a d theta there, over 9 plus 4 is 13 plus 12 cos theta to the power 3/2. 0.065146686. Okay, and then you multiply this by this whole thing. Well, this one 4 pi cancels, so you basically just have 4 times that. So you're going to have 4 is equal to 0.2606 times 10 to the minus 7 Teslas. Okay? So this is how you can do a semicircular arc and a point not at the center. What if the arc looked like this, a complete circle, and you wanted to find the magnetic field 3 meters away? How is this going to contribute to that? So we get the current is going this way, right? So how does this part contribute? We have here dl and then r hat. What happens here? When you do dl cross into r hat, you get out of the board. So something is interesting is happening here. If you visualize this half of the circle, this one is, the loop is going this way, and if you do a little piece dl crossed into r hat, you get into the board, right? If you do this half of the circle, dl cross into r hat, okay? Let's do the point right here, cross into r hat. Let's say over here, dl cross into r hat, dl cross into r hat, dl cross into r hat. So what is the direction? So for this part of the circle, the magnetic field is into. For this one, it is dl crossing r hat out of the board, dl crossing r hat out of the board, dl crossing r hat out of the board, dl crossing r hat out of the board. So this one contributes out of the board. So they're going to fight against each other. But in reality, together the pair should work in the same direction, right? Because if you think about this right-hand rule, curl your fingers in the direction of the current flow, the magnetic field it creates inside should be into the board, and then they should be coming out, right? So over here, the magnetic field everywhere here, the total magnetic field should be into the board, then it should curve around, and then over here it should come out, right? So we would expect the coming out one here to win over the going into magnetic field, because this acts like a magnet. The field goes in, wraps around, and then comes back out, right? So what we're going to have to do is we're going to have to say, if it's a complete circle, I'm going to have to take the magnetic field of this one. This is into the board, into board. Then you're basically going to have the same equation, but now it's a negative x, right? Because the x is on this side. Instead of being on that side, it's a negative x. It's on the other side of the center. So you have the similar looking equation, but wherever there is an x, we replace it by negative x. So the equation becomes 2 minus 3 cos theta over 13 minus 12 cos theta to the power 3/2 d theta. So what did I do? The R stayed the same, R is R. Instead of plus 3 cos theta, I made it negative 3 cos. And then over here, I also changed the x to negative 3, 13 minus 12. Now let's calculate that magnetic field. This is going to be out of the board. Out of board. Okay? And then see what's going to happen. Negative 0.288786. Okay? And the reason it's negative is because this part is 2 minus 3, this part is a negative number. And then when you multiply this by this thing, this one comes out B for this part of the circle, like this. Of course, I have also the 2 from doubling the integral, right? So multiply this by 4, and you get, and then what's the meaning of the negative? Let's just take its absolute value, and let's say this is out of the board. Or we could say negative into the board, but it's just better to say out of the board. Out of board. Okay? So what is the total magnetic field? Okay? So the total magnetic field is 0.2606 Teslas into the board was the magnetic field created by this side, right? And then the magnetic field created by this side over here was bigger, but it was out of the board. So the out of the board wins, right? So we have B total is equal to this 1.1551 minus 0.2606 minus 0.2606. So it's going to be 0.8945 times 10 to the minus 7 Teslas out of board. Right? So the field goes in, wraps around, comes out of the board. The out of the board wins. What if I want to find the B field 1 meter this way? Okay, 1 meter this way. So what I do 2 of these integrals. One plus, but of course the numbers change, right? What happens? So let's do that integral. To board. Okay, now we do this side and we put a negative 1. We put a negative 1, and then this one we put a negative 1. So we just simply go change the integral slightly. Now is that into the board or out of the board? If you do this integral, right, dl r hat, it's into the board, right? It's not on the other side. dl r hat into the board. So they both are into the board. So this time they're not competing against each other. The fields of both of them wrap inside, they go in and then they wrap around. So since x is equal to 1 meter, I'm actually inside. So I just simply add both of them. 6.103 plus 3.321, and I get B total 9.424 times 10 to the minus 7 Teslas into board. Okay, so the magnetic field is very strong on the inside, especially as you go towards one of the sides. The magnetic field increases, but as you go outside, they compete against each other, and the field wraps around and it gets weaker on the outside. So now you know how to do the magnetic field pretty much anywhere inside and anywhere outside. Okay, so hope this helps. Thank you very much.